Good day everyone, my name is Kito Bilid of BSCC 3A, and today we're going to talk about my assigned topic, which is the single carrier frequency division multiple access in my performance task 11. So let's go over to LTE key parameters. So this slide provides an overview of LTE key parameters. First of all, the frequency range. For LTE, it can be operated in the FDD and TDD bands of UMTS. Then we have channel bandwidth defined as 1.4 megahertz, 3 megahertz, 5 megahertz, so on and so forth. Modulation schemes that are available for LTE downlink is QPSK 16QAM and 64QAM. In the uplink, we have the 64QAM, which is optional for handset. To support multiple access schemes for LTE, we have OFDMA in the downlink and SCFDMA in the uplink. Now, introduction. In the uplink, there is a transmission scheme which is known as single carrier frequency division multiple access. So what does this mean? First of all, we have seen that OFDMA got advantages but also disadvantages. The major disadvantage of OFDMA is the high peak to a power average ratio, also known as crest factor. This is the result as this transmitted signal is the sum of a modulated subcarriers, and the sum of them are in phase. High amplitudes are not avoidable. The high peak to average power ratio requires high resolution digital analog and analog digital converters, as well as a very linear transmitter circuitry, as any non-linearity will cause in that modulation distortion, raising phase noise, causing intercarrier interference and out-of-band spurious saturation. This is already challenging in a downlink where we do have no trouble in providing power or space for the design on the terminal sides. So this is nearly an overkill. The goal for 3GPP was to select another transmission technique for the uplink that keeps the advantages of OFDMA, which is multi-carrier transmission and therefore an efficient use of the available bandwidth, and combines this one with the advantage of a single carrier transmission, which is compared to multi-carrier to lower peak to power average power ratio. As the name already emphasized, this is achieved with single carrier FDMA. Now, how is a SCFDMA carrier generated from a high-level perspective? First of all, there's another block in the signal processing chain. A discrete Fourier transform is performed on the data symbols after serial parallel conversion, which transfers them from time to time into the frequency domain. Afterwards, there's subcarrier mapping as in OFDM and IFFT to transfer the signal from frequency domain into the time domain. After the parallel serial conversion, the cyclic prefix is inserted. The last two blocks are the same as for OFDM, so there's no difference to the downlink signal generation chain. The DFT precoding is the essential difference between downlink and uplink. So what does DFT do? Well, first of all, it is a mathematical operation, but compared to OFDMA in a downlink, where each subcarrier carries just one specific modulation symbol, the DFT takes the symbol and spreads this one over the available subcarrier in that meta. Each subcarrier carries a portion of superposed symbols, therefore, single carrier FDMA is also referred to as DFT spread OFDM. So this picture visualizes the things we just learned very well when we compare classical OFDMA using the downlink and SCFDMA or DFT spread OFDMA for the uplink. Then we can say that an OFDM, each subcarrier carries only information related to one specific symbol. So this is indicated by the color used for these subcarriers, as you can see on the left-hand side of the graph. In a single carrier FDMA, each subcarrier contains now information about transmitted symbols. You can see on the right-hand side in the graph that each of the different subcarriers carries now a little bit of a red, green, blue, orange, and so on. With this, it means that with performing a DFT precoding, we shift around the problem of high amplitudes due to subcarries in phase. Now, the question that comes up is how the subcarrier mapping is realized in the uplink. So there are two possibilities, each coming with one advantage. First, we do have localized mapping in localized mode. The modulation symbols are assigned to adjacent subcarriers as shown in the graph. This would give us the advantage of multi-user scheduling gain in the frequency domain for localized subcarrier mapping. Single carrier FDMA is named as localized FDMA. The other mode, user distributed subcarrier mapping, and that meta, single carrier FDMA, is referred to as interleaved FDMA. In this mode, the modulation symbols are equally spaced over the entire bandwidth. The advantages of this mode based on the robust transmission of control channels and the support of high mobility of the terminal. Now the question is, which of the two modes is realized within LTE? And this decision was that the localized modes fit better to the overall system requirements. Further, both modes are impacting the peak to average power ratio differently. Again, the goal of introducing single carrier FDMA in the uplink was to lower the peak to average power ratio, enabling an efficient power amplifier design for the device. So this chart shows the complementary cumulative distribution function, which describes the probability distribution of the peak to average power ratio. The CCDF is displayed for OFDM. So for the downlink and for both modes of single carrier FDMA, a localized and an interleaved FDMA. This data is taken from an article published in IEEE Trouble magazine back in September 2006, so in the very early days of LTE definition. The simulation uses a system with 256 subcarriers in a 5 MHz channel, where 64 subcarriers have been assigned to the user, which are in case a QPSK modulated. And in case of B, okay, wait, oh, and in case of B, it is 16 QAM modulated. Further pulse shaping was applied to the signal or not in difference. 2G and 3G, there is no filter definition. LTE means this is open to the design engineers. Just define in channel requirements, for example, modulation capability measured within the EVM and out of channel requirements, adjacent channel leakage power ratio, or spectrum emission must need to be passed by the transmitter design. In this simulation, a route raised cosine filter was used with a roll-off factor of 0.5. As we can see, the crest factor for OFDM is constant at around 12 dB, which is comparable to Ymax, and it is independent from the modulation schemes and the used filter. This is different for single carrier FDMA, especially for interleaved FDMA. For localized FDMA, which is the blue line, which is the mode which is used in LTE, the peak to power to average power ratio is in case of QPSK modulation around 8 dB, and therefore 3 dB lower than OFDM. For 16 QAM, the difference is just around 2 dB. So let's go over to SCFDMA parameterization. So LTE uses two modes, frequency division multiplex FDD and time division multiplex TDD. The parameterization in the uplink is for FDD, the same as in the downlink. The two different cyclic prefixes are used normal and extended, giving 6 respectively 7 single carrier FDMA symbols in the uplink. For TD-LTE, the usage of the uplink depends on the selected uplink-downlink configuration. By each configuration offers a different number of subframes assigned for uplink transmission, but the parameterization of those subframes is of course equal to FDD mode and depends on the selected cyclic cyclic prefix. So let's go over to the summary and conclusion. So SCFDMA is a new multiple access scheme that is currently being adopted in 3GPP LTE uplink. SCFDMA utilizes single carrier modulation and frequency domain equalization and has similar performance and essentially the same overall complexity as those of OFDMA system. A salient advantage over OFDMA is that the SCFDMA signal has a lower power average peak ratio because of its inherent single carrier transmission structure. So SCFDMA has drawn great attention as an attractive alternative to OFDMA. SCFDMA has two different subcarriers mapping schemes, as I've discussed, which was distributed and localized. In distributed subcarrier mapping scheme, users' data occupy a set of distributed subcarriers, enriching frequency diversity. In localized subcarrier mapping schemes, users' data inhabit a set of consecutive localized subcarriers, enriching frequency selective gain through channel-dependent scheduling. The two flavors of subcarrier mapping schemes give the system designer a flexibility to adapt the specific needs and requirements. So SC FDMA also bears similarities to direct sequence CDMA. An advantage of SCFDMA over this is the ability to utilize channel-dependent resource scheduling to exploit frequency selectivity of the channel. So that's all for today. Thank you.